Okay, so we are going to start problem number 5. Okay, so this is problem number 5. And what does problem number 5 say? It says that a bucket is tied with a rope and it is rotated in a vertical plane. And let us assume that this vertical plane is, for our convenience, the YZ plane. The length of the rope R rotating with the bucket is proportional to the angle theta. So you have the dependence of R is equals to k theta, where k is equals to 1 meter per radian. Okay, and the problem states that the time dependence of theta is theta of t is equals to theta naught into exponential of minus of beta t. And a block of mass m is kept inside the bucket. So this is the bucket actually, or it's not a very nice diagram in the sense that this is the bucket and there is a mass m that is kept inside the bucket. Probably it is spiraling or rotating about in this certain axis. So the gravitational acceleration due to the earth is g, and g vector is equals to g of minus of y cap. So this is your YZ plane. Let me draw the YZ plane here. And your acceleration to gravity points along this direction. The friction coefficient between the surface of the bucket and the block is mu. So the first part of the problem actually asks you to sketch the position of the bucket in the r theta coordinate system. This part is what I'm not going to do. I'm going to leave this as an exercise because it is quite instructive to plot this diagram in an r theta plane to have the parametric plot between r and theta. But just as a hint, the functional dependence of r upon theta is r is equals to k theta. You see that the domain of r ranges from 0 to infinity, and so theta also ranges from 0 to infinity. And obviously, since k is greater than 0, especially since it assumes a value of 1 meter per second, as your theta increases, so does r. So you can guess that the figure of the r theta plot is going to be a spiral, and the spiral is going to be an outward spiral. So I encourage you to draw this plot, this r theta dependence or the r theta plot in using any graphing software or whatever you have, and you can plot for different values of theta. For example, say ranging from theta is equals to 0 to 2 pi, 0 to 3 pi, 0 to 4 pi, increasing, and you will see that the emergent figure is that of a spiral. So we'll go straight into the part B of the problem, which asks you to solve for the critical angle theta c at which the block just starts to slide inside the bucket. So there is the bucket and there is the block. So either way, we are just going to find the critical angle theta c during which the block is just about to slide inside the bucket. That means with respect to an observer, let this be an observer who is standing in this bucket, and with respect to the observer who is co-rotating or co-moving along with the bucket, he sees the block to be at equilibrium. That is, with respect to an observer inside the bucket, the block is just at equilibrium, and you're required to find the critical angle theta c at the point of which the block is just about to slide inside the bucket. So you see that it is kind of preferable to solve this problem in the frame of the bucket, or with respect to the observer who is co-moving with the bucket or who is stationary in the frame of the bucket. So let me first of all start with a coordinate transformation. For example, and this is quite generic. So there are two kinds of observers, right? The one observer who is standing in the inertial frame. That is, let this frame be the inertial frame. Let me denote it by I. and this is the frame attached to the bucket. So this is the bucket frame, and let there be any generic object of mass m which has a certain trajectory inside, in this certain plane. Let me draw it even better. So this is the trajectory of the mass m as viewed both by observers standing in the inertial frame and by observers in the bucket frame. So the position vector of the mass m with respect to the inertial frame is denoted by r mass with respect to the inertial frame, and the position vector of the object with respect to the bucket frame is denoted by r mass with respect to the bucket, and the position vector between the bucket and the inertial frame is given by r bucket with respect to the inertial frame. So by simple vector algebra, you can work this out, that r position vector of the mass with respect to the inertial frame is equals to position vector of the mass with respect to the bucket plus the position vector of the bucket with respect to the inertial coordinates. So the position vector of the mass with respect to the bucket is equals to the position vector of the mass with respect to the inertial frame minus of the position vector of the bucket with respect to the inertial frame. Now you can take total time derivatives of this, and you can find that the acceleration of the mass with respect to the bucket frame is equals to the acceleration of the mass with respect to the inertial frame minus of the acceleration of the bucket with respect to the inertial frame. So these are the quantities that you need to find, and these are the quantities that you need to know, these three quantities. Okay, so the first question, so what is the acceleration of the mass with respect to an observer in the inertial frame? So as you can see that the bucket is rotating and its dependence is given by r is equals to k theta, where the time dependence of theta is also given. Okay, so a person who is standing in an inertial frame, he'll observe that the mass only has an acceleration due to gravity, nothing else. He will not feel any inertial forces, or he will not attribute any inertial forces of Coriolis, centrifugal, pseudo acceleration whatsoever. Any inertial acceleration will not be attributed by the inertial observer onto the mass. So the only acceleration that he can attribute to the mass m is just the acceleration due to gravity, which is g of minus of y vector. So the acceleration of the mass with respect to the inertial frame is g of minus of y vector. Okay. Now the second part of the thing asks you to find out, you have calculated the first part, that is the acceleration of the mass with respect to the inertial frame. Now the r as well as the theta dependence with respect to time of the bucket in the inertial frame is given to you. Is given. And what exactly is the information? That theta as measured, theta which is the angular dependence of the bucket with respect to an observer in the inertial frame is given to you, and that value is theta naught into exponential of minus of beta t. And r, which is equals to theta, since k assumes the value of 1 meter per radian, r also assumes the value theta naught into exponential of minus of beta t. From this you can calculate the theta dot and theta double dot. From here you can calculate r dot and r double dot. Very good. Now the acceleration in the polar coordinates is given as and I'll just write down the the expression that the acceleration is equals to r double dot minus of r theta dot square of r cap vector plus of twice of r dot theta dot I don't know okay, theta double dot of theta cap. Good. So this should be a plus sign. Okay, yeah. So these quantities like r double dot theta dot and r, as well as r dot theta dot r and theta double dot, can be calculated from the so-called, from these given, from the given time dependence of both r as well as theta. So now the acceleration, so this is the acceleration in the polar coordinates, right? So the acceleration of the bucket with respect to the inertial observer is given by r double dot minus of let me just write the explicit time dependences as well, minus of r of dot theta dot of t whole square of r cap plus of twice of r dot of t theta dot of t plus of r of t theta double dot of t theta cap. And so finally from this expression what you have derived is this, and as well as this. So the acceleration of the mass m with respect to the bucket, this you can easily find out right now just substituting the values of this and this into the equation x1. And if you do that, you can find that the acceleration of the mass m with respect to the bucket frame is, and I'll just list down the result. It is just equals to minus of, okay, one more thing, I'll do it step by step. So this is equals to minus of g sine theta r cap minus of r double dot minus of r theta dot square of r cap minus of g cos theta theta cap plus of twice this will be a minus of twice r dot theta dot plus of r theta double dot theta cap. Now obviously these particular terms come about from just the just if you break down the y's the y cap unit vector in terms of r cap and theta cap, which I strongly advise you to do, you'll get these two particular expressions. So g of minus of y cap will be broken down or decomposed into this and this form. So I'll leave it to you to fill up these details, and rearranging, what we finally get is that the acceleration of the mass with respect to the bucket frame is equals to minus of g sine theta minus of r double dot plus of r theta dot square of r cap minus of g cos theta plus of twice r dot theta dot plus of r theta double dot of theta cap. So now you have found out the acceleration of the mass with respect to the bucket, and it has a radial component which we are going to name as the acceleration, the radial acceleration of the bucket, of the mass m with respect to the bucket, and this is the tangential component which we are going to name as the tangential component of the mass with respect, tangential component of the acceleration of the mass with respect to the bucket frame. So our acceleration vector of the mass with respect to the bucket frame is equals to the radial component part plus the tangential component part. Let me write down the tangential component part. Good. Now just looking at the figure, now we have to deal with the physics. So this is the acceleration of the mass with respect to the bucket frame. Okay, so there is an observer who is standing inside and who is stationary with respect to the bucket. He sees that there is a mass m, right? And he sees that the mass m is at rest, that is, it is at equilibrium, but it is just about to slide, right? So there is, he perceives, what he measures is that the acceleration component there is one of ar of m comma b. That is what he measures, that is the acceleration of the mass with respect to the bucket. He measures these two components, right? This one and this one, and this is A of theta of the mass with respect to the bucket. Now obviously the point is that the magnitude, I mean this A of r of the mass with respect to the bucket, this should be greater than 0, right? Because if it was less than 0, then it would have pointed out in this direction, and that means the normal reaction would have been 0. If the net acceleration as perceived by this observer on the bucket was in the minus of r cap direction, then the bucket would have just flown off. It would never have been at equilibrium or at rest. So it needs the acceleration, the radial acceleration needs to point in the r cap direction, and A of r, that is the radial component of the mass with the bucket, needs to be greater than 0, so that the acceleration, so that there is a kind of a force attributed to the r cap direction, so that there is a net resultant, so that there is an effect, reaction effect by the normal force. So that is the particular, that in a sense gives you the notion of the magnitude of the AR component. Okay, now we'll just go ahead and draw the free body diagram. So this is the bucket, and this is the mass m. The force along this direction is given by my m of AR of the mass with respect to the bucket, and this is mg minus of y cap, which you can decompose again into the r cap and the theta cap direction. This is ma theta of the mass with respect to the bucket. So what will be the normal the normal reaction? The normal reaction is going to be in the minus of r cap direction. So the normal reaction is going to be MAR of the mass with respect to the bucket minus of r cap direction. And let me just list down the result. It will be equals to minus of m minus of g sine theta minus of r double dot plus of r theta dot square r cap. And obviously you can see one more thing, in the sense that that the normal reaction is right now pointing in this direction. This is your normal reaction r vector. So the friction, so the job of the friction is to oppose any relative motion. Okay, so whatever kind of force is there, the force that tries to move the body or move it out of equilibrium, the friction will point out in the opposite direction just to oppose any kind of relative motion. And the magnitude of the friction, as you are all aware, is equals to mu times the magnitude of r, and this will oppose any force. It will try to oppose any relative motion between the block and the base of the bucket. So what you have is theta of t as a function of both time as well as radius. So theta, this is equals to exponential of minus of theta naught into e to the power minus of beta t, and the radial distance with respect to time is also theta naught into e to the power minus of t. And from that you can calculate, as well as just I have pointed out earlier, is that you can calculate theta and theta double dot as well as r dot and r double dot. So you can impose these values into the normal reaction, and you can find out that that the condition of just sliding is that this ma theta points out in this particular direction, right? So the friction should point out in this direction just to oppose any kind of relative motion. So this is your friction. So frictional force, and the frictional force should be the magnitude times minus of theta cap. If your ma theta with respect of the that the tangential component of the acceleration of the mass with respect to the bucket, if this is greater than 0, then it points in the theta cap direction, and then the friction points in the minus theta cap direction. If this quantity is less than 0, then it points, then the mass times the acceleration of the tangential component of the acceleration of the mass with respect to the bucket points in this direction, and in order to oppose any relative motion, friction has to point in this particular direction. So friction will just try to oppose any relative motion. So I mean, we are assuming the case when ma theta of the mass with respect to the bucket is greater than 0. It can also be less than 0 depending upon the values of the angle and whatsoever, but let us just assume that it is greater than 0, and for that point friction points in the opposite direction of minus of theta cap. So if you now put down, so what is the condition of the condition of sliding? The condition of sliding, just about to slide, is that mu times the magnitude of r is equals to m times a theta of the mass with respect to the bucket, and we know this quantity. This is equals to m of g cos of theta plus of twice of r dot theta dot plus of r theta double dot. Now if you put in the values of r theta, theta dot, r dot, theta double dot and r double dot, you can express these. It's just a little exercise to put in the values, and what you will get out of this condition is that mu of minus of g sine theta minus of r double dot plus of r theta dot square is equals to g equals to g cos of theta plus of twice of r dot theta dot plus of r theta double dot, and just put in the values of theta r dot theta dot square r whatever you have to put in those values, and I'll leave it to, and just go ahead with the algebra. It's pretty simple algebra again. So the condition, I'll just list down the answer, is equals to theta minus of beta square theta plus of beta square theta cube is equals to g cos of theta plus of 3 beta square theta square, and the equality is exactly at the point theta is equals to theta c, that is the critical angle. So you have to find out the critical angle when this equality of equilibrium or rest condition is satisfied. If the rest condition is not satisfied, then this won't be an equality. There will be motion, it won't be at rest. And if you solve this particular equation, you will get the required values of theta. And I won't go ahead and list down the result, so it's just a matter of solving this equation, solve for it and find the value of the critical angle. Okay, so this concludes the problem number 5, and okay, thank you for listening.